Hi everyone, welcome back to Chapter 5, Part 2. In this video, we are going to explore how gravity, tension, and normal forces are defined, in addition to exploring the idea of net force, which is where we need to add up the contribution of all forces in a given system. And as we do that, as we add up all those forces, however many we happen to have, those forces are going to tell us how our mass will accelerate in the system. And because I'm not a big fan of trying to do everything at once, we are going to break these down into X and Y systems. So we'll look at summing up all the X components of all of our forces to tell us how our mass will accelerate along the X direction. Likewise, we will sum up all of the Y components of our forces to tell us how our mass will accelerate along the Y direction. So let's start off with gravity. Now, we may already know about gravity. We know that gravity has a value of 9.8 meters per second squared. And this acceleration value, keep in mind that this number is the magnitude of gravity. The sign on G is the sign on the number. And so gravity does not become negative until we define a reference frame in the system. So if my reference frame says that up is the positive direction, then we are dealing with a value of negative g. But if my reference frame says that down is the positive direction, then we are dealing with a positive g. So that information is going to carry forward into the idea of our gravity force. And there are different books that want to describe all the different forces that we're going to see. In addition to gravity, our tension force, our normal force. When we get to Chapter 6, there's going to be friction force. And so I've seen some notation where they will use subscripts of F sub whatever that force happens to be. So F sub G could be the gravity force, F sub T tension, F sub N, and so we have all these different force terms that have the appropriate subscripts. But if we don't carry the proper subscript along, then we're going to lose out on the information, and it doesn't take much for us to mess up one of these expressions along the way. And so my preference in describing these forces, I will actually write out the gravity force as mg. And this is because gravity by itself is such an important value that it's worth having in the problem statement, because later on we may end up introducing other terms that also depend on gravity. And if we can see gravity written out with respect to the different terms in our expression, then we may be able to condense some of the work that we have. So I will be using mg every time that I talk about a gravity force. As for the other forces, I prefer to just use the letter that each of those forces starts with. I'll use capital T for a tension force, capital N for normal force. And then friction, well, friction starts with an F, but I'll use a lowercase f to denote that friction force. And so this way, it's a lot easier to keep the different forces separate from one another in the algebra until it comes time to insert our numerical values. And so our gravity force, also known as weight, mg, do keep in mind that weight is not the same thing as mass. Weight is the force of gravity that acts on mass, but mass is just mass. All right, well, that might seem like that's all we have to do. All we have to do is write down mg. Mg is always going to point down because our acceleration due to gravity is always going to point down. But later on in chapter 6, what we're going to find out is that we are not going to be able to use mg for every case scenario that involves gravity. We are using the value of little g, 9.81, and we say that gravity is a constant, or at least Newton said that gravity was a constant, and from there he was able to derive his kinematic equations. But as it turns out, the acceleration due to gravity is not a constant. We can assume the acceleration of gravity to be constant at the surface of the Earth. So at the Earth's surface, we will use the value of 9.81 meters per second squared. But if we travel away from the surface of the Earth, say to a space station or to another planet, well, now we can't use this value of gravity anymore. The only time that we get to use this value is when we are at the surface of the Earth, and if we are maintaining a relatively close position with respect to the surface of the Earth. And that works out okay for all of the previous problems that we've been doing. You know, we've had problems where we dropped something off of a cliff. In that case, we were only displacing maybe 30 meters or more. But even if you had something happening in an airplane, you're still relatively close to the surface of the Earth in comparison to, say, something up on a space station, like the International Space Station. So we want to see, what does gravity behave like when we're not at the surface of the Earth? And this is another expression that Newton derived. Newton, in addition to being a mathematician, a physicist, he also dealt quite a bit with chemistry, optics, astronomy, and even alchemy. Obviously, he didn't get anywhere with the alchemy, but nobody's perfect. But during his studies with astronomy, he had access to a lot of observational data that was passed down through multiple decades from individuals like Kepler, Brahe, and others. And when you have enough data in front of you and you can start analyzing that data, you can start to form expressions that reflect the patterns in this data, and that's what Newton did. And what Newton found out was that this force of gravity, which I'll go ahead and write it as F of G right now, because if we're not on the surface of the Earth, we can't use mg anymore. So I'll use the F sub G term as a more generic version of that expression. What Newton found out was that if you had two objects out in space, like maybe the Earth and the Moon. So here's the Earth and the Moon. There was a certain amount of gravitational attraction or gravitational force acting between these two objects. And it didn't even have to be the Earth and the Moon. It could be the Earth and the Sun. It could be Jupiter and one of its moons. It could be, one of the other planets in our system and the Sun. It really didn't matter. All that mattered was that if you had two masses, mass 1 and mass 2, separated by a given distance, r, there would be this inverse squares relationship where the further away you get, the more the force diminishes. And Newton was able to figure out the magnitude of force between these two objects. Now, he was missing one very important piece, and the first thing that you might notice in all of this is that if you look at the units don't match up in this expression, at least not yet. For force, we have units of what we're going to call newtons. And I just now realized that we did not cover the units of force in the previous video, so we'll do that right now. Our unit of mass, our SI unit of mass, is going to be the kilogram. And as we already know, we have meters per second squared for acceleration. All of those units, we are going to cram together into a single unit that we call a newton. And so over here, we have a newton for force. And on the right-hand side, we have two mass terms in the numerator. That's going to give us kilograms squared. And then we have an r squared value. R is going to measure the distance between our objects, and since it's squared, then we need meters squared. And if you try to deconstruct the unit of the newton, you can obviously see that we do not have the right combination on both sides. And so this means that there's a missing term. And Newton also realized that because whenever he would plug in the numbers for the masses of these objects and their separation distance, he was getting values that were just way too big. So there's a missing term here, and the way that we can solve for that missing term, the way that Newton was able to solve for that missing term, was he just took the ratio of everything that was already present in the expression. He took the measure of force on the left, he divided by the combination of the masses and the separation distance, and this ratio had to equal whatever the missing piece was. And surprisingly, no matter what combination of masses and separation distance and force that Newton used out of all of this astronomical data that he had access to, this ratio kept coming out to be the same number every time. And so he called this big G. This was the universal gravity constant. So that's the missing piece of the equation. This is the missing number that is going to make everything work out right. And the value of big G was 6.67 10 to the minus 11. But now we need some units for big G. Now again, we can go back and we can deconstruct the units for a Newton, and we can try to figure out what needs to go in place for big G, but there's actually a much quicker way of figuring out what the missing units are. And that is to just use what is already present in the expression. On the left side, we have units of newtons. And then we have an equal sign here. So I need whatever's on the right to equal a newton. Okay, well, I don't have any newtons on the right-hand side right now, so I'll put one in. And right about now, your old math teacher is having a conniption, because first thing we learn about math is what you do to one side, you have to do the other. But hang on a second. There is some method to my madness. So we have a newton on the left. We now have a newton on the right. And that's all I need, is the newton. So what do I do with all the rest of this stuff? Well, let's get rid of it. How do we get rid of it? Well, we can get rid of that by multiplying by the inverse of that unit set. And so now, by looking at everything that we have for the units of G, paired with the units of our masses and our separation distance, everything now works out to give us a true statement. So the units of big G are a Newton meter squared kilogram squared. And we now have a new and improved expression to describe the force of gravity. And this expression can be used anywhere in the universe. It can be used out in space, it can be used on another planet. We can even use it here on the Earth's surface if we want to. The one thing that we need to discuss, or at least clarify, is this value of R. Right now it looks like R is the separation distance between the two surfaces, but it actually needs to be measured from the center points of the two masses. And this actually starts to become more and more critical as the two objects get closer and closer together, because the actual separation distance between the Earth and the Moon, I'm just throwing out a very approximated value here, but it's about 300,000 kilometers from the Earth to the Moon. And if we were to look up the radius of the Earth and the Moon, so I'm going to go ahead and get out my phone and just Google these values real quick. Radius of Earth in kilometers. And that is coming out to be about 6.37 kilometers. Excuse me. That is not right. Sorry. Got my decimal and my comma mixed up. Sorry. Yeah, that would make for a very small Earth. 6.37 thousand kilometers. There we go. That's better. And then we need radius of Moon in kilometers. So 1,737 kilometers. So let's take that value along with the separation distance between the two surfaces, and again these are very rough estimates. The moon is not always the same distance from the Earth. It varies a little bit during the orbit. But I'm going to add all these numbers up. We have 6,370, 1,737, and 300,000, which is going to give us that many kilometers center to center separation. Now, if we were to not include that center to center separation, so in other words, if we were to just use the 300,000 kilometers, we would only be off by about 2.7%. So that would roughly be the margin of error, 2.7%. And you might be thinking to yourself, well, that's not so bad, except are you going to be willing to risk having that amount of error if you're working for someone like NASA and you're trying to launch a mission to the moon or land something on the moon? Well, in that case, an error like this is absolutely an error like this is going to be absolutely unforgivable. This is way too high. For NASA, you're going to be looking at least a 6 sigma scenario where your margin of error would have to be about 6 standard deviations away from the average, and that can be difficult in and of itself to achieve. But then you have to consider all of the components and the moving parts and the software, all of that stuff that has to work together, and having even just a 3% error is just unforgivable in terms of what NASA is going to accept. And so in this case, for our class, it's an introductory class. Having an error of about 3% may not be that big of a deal, except if you haven't noticed yet in your homework, usually the error that is allowed in most of your homework problems is about plus or minus 2%. And so, well, that's not going to work for us. So we do need to have that center to center separation distance as the measure for R. And the reasoning for this will be further explained when we get to chapter 9 and we start talking about center of mass. And the idea of center of mass is basically take all the mass of your object and squeeze it down to a single point in space. And that single point will usually be right in the center of your object, give or take a little bit due to symmetry. But if we were to treat the Earth and the Moon like points in space, and we had all of the mass at those points, well, now we can see the importance of having that separation distance, including the radius of the two objects. So if you're still not sure about that, we'll try another example here. Let's try applying Newton's universal law of gravity, and that is what this expression is called. We have our universal gravity constant, and so that is going to be plugged into this expression as the universal gravity equation. And in some books, this is even called Newton's fourth law of motion. But the universal gravity law just has kind of a better ring to it. So universal gravity law, or I've also seen it called the universal law of gravity. But now we want to use this to measure our weight at the surface of the Earth. And that's something we already know how to do. We said as long as we're at the surface of the Earth, we can use mg. Okay, so I'll volunteer myself as a part of this little thought experiment. So what we need, at least here, is mass of me, mass of Mike, times the acceleration due to gravity, which is 9.81 meters per second squared, and that will give me the value of my weight. And remember, weight is just a more common way of saying force of gravity. So I have my mass times gravity, and yeah, I could measure my mass, I could multiply it by gravity and get a number, but the purpose of this discussion is to make sure that this is working. So now I need the value of big G. And mass 1 and mass 2. Mass 1 and mass 2 are the two masses that are involved in the system. Well, I have my mass, so I'm part of the system, and I'm standing on the Earth, and so the Earth is the other mass in the system. So we'll put both of those in, and I can look up the mass of the Earth. I can Google that if I need to, and then distance between us squared. Okay. Well, now if you look, my mass is on both sides of the expression, and so I don't have to embarrass myself and tell you how much my mass is, because everything in this expression is now going to reduce and basically just tell me what the measure of the acceleration of gravity is at the Earth's surface. Now here's why the center to center separation distance becomes so important. So R has to be measured center to center between the two masses. And if we look at the case scenario of me standing on the Earth, if we were only to measure the separation distance between the objects, well, I'm standing on the Earth, I'm touching the Earth. The separation distance between me and the Earth is 0. And if I try to plug that into the expression, well, then I'm trying to divide by 0, and that doesn't work. But again, that's why we have to have a center to center separation distance. And basically what we have here is the radius of the Earth plus an extra meter or so to get to my center point. And so obviously with the radius of the Earth being, what was it? 63 or 67? 6370. With the radius of the Earth being 6370 kilometers, I don't think that extra meter is going to make much of a difference. And so I'll just use the radius of the Earth as the center-to-center separation distance. And so this is why the value of little g is used exclusively with all of our problems that involve physics that are occurring at or near the surface of the Earth. Because now, even if you were to have a physics problem involving a plane that was about 30,000 feet up, that would be, let's see, 30,000 feet, divide that by 3, so that'd be about almost 10 kilometers up. So you'd have to add 10 kilometers to the 6,370 kilometers of the radius of the Earth, and so you'd get about 6,380 for the center-to-center separation of the plane and the Earth. But if you were to compare those two numbers, and I'll get my calculator out for this, the comparison between those is not going to be all that considerable. In fact, this comes out to be about 0.16% difference. And so for us, that is well within the plus or minus 2% error that Wiley will accept. And so as long as we're, I'd say, within the Earth's atmosphere, anything between the surface of the Earth and the Earth's atmosphere, we can use little g as equal to the combination of all these values. Now, if you were to look up the mass of the Earth, the radius of the Earth online, you're probably going to see a pretty varied range of values. And that's because, first of all, the radius of the Earth is a little bit bigger at the equator than it is at either of the poles, and that has to do with the Earth spinning. The Earth will literally throw some of its mass out. And so typically what you have when you look up the radius of the Earth is an average value. And then the mass of the Earth itself is a calculated value, and different people performing the same calculations are going to have slightly varied values. Add to that the fact where exactly on the surface of the Earth are you going to measure for R? Because you have areas like Death Valley that are, a few hundred feet below sea level. You've got places like Mount Everest, which are a few miles above sea level. But, I've said that term twice already. Why don't we measure this at sea level? And so the value of G is calculated as what the acceleration of gravity is approximately at sea level at the Earth's surface. So again, if you go online and you find values that you can plug in here, based on the values that you get, you're probably not going to calculate exactly this value, but it's going to be really close. And so the next thing that we might try is let's ask ourselves, well, what is gravity up at the International Space Station? And so we have astronauts that are up there at the International Space Station, and the the space station itself is only about 300 kilometers above the surface of the Earth. It's really not that far away. And we'll talk in the next chapter about how they're able to maintain that altitude without falling down. But what we have here is radius of the Earth plus an extra 300 kilometers. And I'd like to know what is the value of the acceleration due to gravity for the astronauts that are up there in the International Space Station. And a lot of people kind of jump the gun and they say, oh, it's 0 because they're weightless. And this could not be more incorrect. Okay, they are not weightless. The term weightless implies that you have no weight. So how does that occur? Well, you either have to have 0 mass, which is kind of the trivial solution, or you have to have 0 acceleration due to gravity. We know now that the acceleration due to gravity is based on a combination of the universal gravity constant, big G, the mass of the Earth, and the separation distance between our two objects. And so the center to center separation distance between these two objects, R, is going to be the radius of the Earth plus the altitude of the space station. This was the radius of the Earth in kilometers plus an extra 300 kilometers gives us 6670 kilometers, or almost 7 million meters. And I want that to be in meters because everything that we plug in for our equations needs to be in the standard units. And let's go ahead and plug all this in. We have 6.67, 10 to the minus 11. That was the value of G. So we go back up to that expression right there. There's the value of G. And that is going to be paired with the mass of the Earth. So now I'll need to look up the mass of the Earth. And again, whatever you look up, you'll probably get slightly different values on your Google searches. So we need mass of the Earth in kilograms. And Google is giving me 5.972 10 to the 24th kilograms. All divided by 6670000 quantity squared. Now there's a lot of stuff that we have to plug into our calculator here, so do take your time. Don't try to plug everything into your calculator all at once. Just take it a piece at a time. And so give me a moment here to and let's see here, I'm getting a value of 8.95 meters per second squared, which is not all that different from the 9.8 that we get at the surface. In fact, this is about 91% the value of gravity that we experience at the surface of the Earth. And I show this to people and they're like, well, how can that be? Every time we see the videos, those astronauts are weightless. They're just floating there. And again, I say that the term weightless is incorrect. A better term for what they are experiencing and what you are seeing is called perpetual free fall. We need to keep in mind that as a force, gravity is constantly going to be pulling that space station down to the ground. But at the same time, gravity is pulling all of the astronauts to the ground at the same rate. And so if you could imagine yourself in an elevator that all of a sudden just started falling, well, you and the elevator would be falling at the same rate, and it would give you the appearance of weightlessness. But unlike the elevator, which, eventually you would reach the ground, with the International Space Station, we have a very delicate balance of the force of gravity trying to pull the space station and the astronauts down, while at the same time the space station and all of its occupants have a velocity that wants to carry them out into space. And so this delicate balance of flying outward and falling in causes this situation of perpetual freefall. And so the effects of gravity are still there. It's just that those same effects are happening to everything, and everything is constantly falling towards the surface of the Earth. And so from a relative perspective or a relative reference frame, it looks like everything is just floating. So don't use that term weightless, because I will ding you for that if I ever hear that, especially if you come and take any of my classes in astronomy. All right, so that concludes our discussion on the gravity force. I know that's probably way more than you were expecting, but I will say that probably 90% or more of our physics problems will deal with situations that are at the Earth's surface, and so we can continue using mg, where g is equal to 9.81 meters per second squared. The other percent of the time, maybe not even 10%, but if we ever find ourselves not on the surface of the Earth, then we will need to use Newton's law of gravity to figure out what the force of gravity is going to be. All right, next on our list is, if nobody minds, and since I'm the one in control of this video lecture, I'm going to jump down to the normal force, just because this one actually goes very quickly with its description, and then we can fill in the remainder of the time talking about tension. So we'll come down to an open spot in our notes right about here. And we'll talk about the normal force. So the normal force, the word normal, it's not going to be the common usage of the word to mean, like, average, but the normal force is actually defined using Newton's third law, where we have equal and opposite forces. In fact, we've already seen the normal force, we just didn't call it that. If we have a mass that is sitting on a surface, in this case it's a flat horizontal surface, and we are on the Earth's surface, this object will have weight. Weight always points down. But from both the third law and the first law, the third law says for every force there's an equal and opposite counterforce. So there has to be a counterforce here, and we were calling that force counter. And the first law says that if we add these two together and we get a net force of 0, then there will be no acceleration. So these are things that we already know, except now we're going to give a name to that counterforce. And that name is going to be, surprise, surprise, the normal force. And so we'll come down here and we will replace the normal force with, or we'll replace the counterforce with our normal force. And what this expression now says is that by adding these two forces together, the normal force will have to be equal and opposite to the magnitude of the gravity force. This is the only way that we will achieve an acceleration of 0. Well, so why do they call it the normal force? In certain areas of math, and particularly in vector math, the term normal refers to a perpendicular relationship. So our surface, we have a horizontal flat surface that our mass is sitting on, and as our mass presses down onto that surface with the weight, the surface in turn has to push back on the mass. And so that surface will point, or that surface will apply its force perpendicular to the surface. We could also use the word orthogonal, but when it comes to normal, perpendicular, orthogonal, I just say what's easier to spell, and normal is easier to spell. So the normal force is a counterforce that points normal to the surface of contact. And this is a necessity right here. Your mass must be in contact with the surface of something else, whether it's a table or a wall or another mass. You have to have that surface-to-surface contact in order for there to be that equal and opposite relationship of Newton's third law. And that's really all that there is to the normal force and in defining the normal force. We can take this a step further, and we can try applying a sum of forces to this system. We can say that the normal force plus the gravity force is equal to 0. But a lot of people have a tendency to look at this picture and they say, well, the normal force is pointing up, and the gravity force is pointing down. Those are vectors that are in opposing directions. Why are you adding them? Well, keep in mind that the notation that we have here for vector addition, vector addition says that you would have to add vectors head to tail. So if I were to add the gravity vector head to tail with the normal vector, okay, well, adding head to tail, we can see right there how the two of them would cancel each other out. But still, most people are not comfortable with this particular notation. So let's try this. Let's take this expression and let's break it down into components. And you might ask, well, why do you have to break it up into components? It looks like everything is happening just in the y direction. Well, now that I can see what the reference frame is for that y direction, I can express everything with the appropriate sign notation. And so now, when I look at adding these two vectors together, I am also going to incorporate this idea that those vectors have directions specific to the reference frame. And that means that my normal force has its magnitude oriented in the positive y direction, while the gravity force has its magnitude oriented in the negative direction. And now, by writing things out like this, a lot of people have a much easier time in visualizing both what is happening in the diagram and in the mathematics. And what this particular expression tells us, we've gone from vector notation to one-dimensional component form. And this tells us right away, if I combine the normal force with the gravity force, which just happens to be in the negative direction, really what we're doing is we're adding those same two vectors. It's just one of them was pointing in the negative direction. And we're getting 0. But this also tells us something kind of important, because if I add this weight term over to the other side, well, now I have a value that tells me what the magnitude of the normal force has to be for this system. And so now we can say, if we have a box of mass 5 kilograms sitting on a tabletop, what's the magnitude of the normal force? So from there, we can draw in the forces that are acting on our mass. We had mg pointing down, we had normal pointing up. We'll put in a reference frame. Technically, I don't need the x frame because there's nothing happening in the x direction. And we now incorporate all of our forces into a sum of forces that reflects the direction of our reference frame, or at least the positive direction in our reference frame. So here we have normal up, that's positive, weight down, that's negative, and the combination of any forces in a system is responsible for how that mass will accelerate. And since this is all in the y direction, then we consider acceleration in the y direction. But we should know better. this mass is just sitting there on the table, minding its own business. It's not moving up or down or left, right, anything like that. It's stationary. So what should we have for this acceleration? We should have 0. And that's exactly what we got up here when we applied the first and third laws of motion. We said we had equal and opposite forces that were providing a net force of 0, which was why there was no acceleration. And so once again, we're back to the same idea of the normal force having to have the same magnitude as our weight. And so we'll go ahead and plug in our numbers. It's the last thing we do. We wait until the very end before we plug in any of our numbers. That's part of the 10-step problem-solving process. We have 5 times the value of gravity, which is about 49.05. And both of these are forces, so regardless of which one we're measuring, they're both going to have magnitudes of 49.05, but they will have units of newtons. So there we have it. There is the magnitude of the normal force. It's equal to the magnitude of the weight. They just happen to be vectors that are pointing in opposite directions. One more quick example with the normal force. What if you were to place your mass on an incline? How would that affect the normal force? So our incline has a certain angle. Our mass is still mass of m. We can plug in a value later. But I want to see what the forces are acting on this mass and how they fit together. Now we're still on the surface of the Earth, so we still have gravity. And remember, gravity always points straight down. But we are in contact with a surface. The mass is pressing down on the incline. The incline has to push back on the mass. But that counterforce has to be perpendicular to the incline. It has to be perpendicular to the surface of contact. So this is the direction that we're going to see that normal force point. And now I pose the question, what is the normal force? Is it still equal to mg? And the answer is no. If the normal force were pointing equal and opposite the direction of the gravity force, then we could say that, but that's no longer what we have. The fact that we're sitting on this incline is creating a vector component issue. So what we should do is figure out, first of all, how do we want to set up a reference frame so that we can break up any of our vectors into x and y directions. Now again, there are plenty of choices as to how you want to choose your reference frame. We've had reference frames like both of these, but don't get too complacent in how you choose your reference frames, because your choice of reference frame should reflect your ability to make the math easier. You don't want to make more work for yourself than you have to. And so as a really good example setting up these sum of force problems that we're going to be working on, I would ask you to always keep in mind the direction that your mass will start accelerating. If you were to place a box like this onto an inclined plane or a slide, which way would you expect that box to start moving? Which way would you expect it to start accelerating? And the answer to that should be downhill. We should expect this to be the direction of the acceleration for that box. So, can you set up a reference frame using X and Y axes in such a way that at least one of those, either the X or the Y axes, is in the direction of the acceleration? Because ultimately what we're going to have to do is we're going to have to break this system up into summations that occur in both the X and the Y direction. And if I can get that acceleration to be exclusively in just one of those directions, then it'll really help with all of the math that we have to do later on. Also keep in mind the direction of your vectors, because those are going to have to play by the rules of your reference frame as well. And from my own personal experience, I'll go ahead and put in the reference frame for this problem. I want one of my axes to be in the direction of the acceleration, so I'll draw my X axes to be in the direction of the acceleration or downhill. In other words, the X axis is running parallel to the incline. For my Y axis, I really only have two options. I can either let it point up to the left or down and to the right. I have to have something that is at a right angle. And with those two choices, I can see that this one is probably the better of the two, because if I let this be my y-axis, well, remember that your normal force was already pointing perpendicular to the incline. And the incline was running parallel to your x-axis, which has to be perpendicular to your y-axis, and so that means the normal force is all in the y direction. And that means I don't have to break my normal force up into any components, because it's all in the y direction. The one compromise that we do have to make is for our gravity vector. Our gravity vector is pointing straight down, and that is in both x and y directions, so I will need to figure out a way to break that up into the appropriate components. The first thing I'll do is I'll just go ahead and draw the components. I need one component that runs parallel to the incline, and I need one component that runs perpendicular to the incline. So a perpendicular component would look like this. You need a component that runs perpendicular to the incline, and then I need a component that runs parallel to the incline. So right there. So this would be the y component of our weight, and this would be the x component of our weight. it would be really nice if I had some kind of angle relationship in here that would allow me to take the magnitude of our gravity vector, which is right here. This part right here is the magnitude of our gravity vector mg. But the only angle that I know for sure is between the x and the y components. That's 90 degrees. That's not helpful. I would either need this angle or this angle. And I can actually get one of those. I can actually get both of them. We need to do a little side discussion. If we think back to our days in geometry and trigonometry, let me see here. I want to make sure I set this up properly. So I have my weight vector, which is made up of its x and y components. And what I'm going to do is I'm going to extend the line for the weight vector and the perpendicular component of that weight. This entire line right here, that is 180 degrees. Okay, any straight line has to have an angle measure of 180 degrees. We already have theta down in the bottom left-hand corner, and our weight vector, let's get a different highlight color here. It's not highlighting very well, but our weight vector is dropping straight down, and that's kind of making a right triangle that's utilizing theta. In other words, I could call this phi, where phi is the difference in 90 degrees and theta. But then we have angles of opposite vertices, which we know have to be equal to each other. So this is also phi. And I know that this component of our weight vector has to be pointing perpendicular to the incline. And so I've already used up 90 degrees of the total 180. That means that all of this, including phi, also has to be 90 degrees, or this little angle in the top corner of our weight triangle has to be the same, has to be the same angle as what our incline theta is using. So that little bit of geometry now tells me what the x and y components of our weight vector need to be with respect to the angle of the incline. The y component, this is the leg that is adjacent to the angle, so that is going to incorporate the cosine. And the x component of our weight vector, the component that is running parallel to the incline, that is the leg that is opposite of theta, so that is sine. Now, everything is about to come together very quickly. I now have all of the vectors, either the vectors or the components of the vectors. Keep in mind, your normal force is a vector, your components of your weight are vectors, even your acceleration is a vector. And so all of these are going to go into our summation of force expression. Because each of these is a one-dimensional summation, I will incorporate plus and minus signs onto my terms that reflect our choice of reference frame. So I'm going to start with the y direction, because I have a normal force that is pointing in the positive y direction. So we have positive n. But then in addition to that, in addition to the normal force, we have the y component of our weight that is pointing in the negative y direction. So we're going to take that, we're going to attach a minus sign to it because it is pointing in the negative y direction. And that's it. That's all I have for vectors that are pointing perpendicular to the incline. And so, like any sum of force expression, we can say that this will equal the mass of the object times the acceleration that it will experience along that axis. But what acceleration are you expecting to see along the y direction? We've already argued that the only acceleration that we should see is in the x direction, downhill. Another way to think of this, go back to the last time that you were on a slide and ask yourself, when's the last time you went down a slide and you just spontaneously flew off? Or when's the last time you were on a slide and you just crashed right through it? Okay, that's what it would mean to have an acceleration along the y direction. Well, we should always be maintaining contact with that slide, and so we should know better, and we should be able to say, well, the acceleration along the y-axis for this system is 0. And with that, I can now say something about the normal force. This expression says the combination of the normal force and that component of the weight has to equal 0, and so the normal force then has to equal that component of the weight. Well, what about the x direction? What's happening there? The x direction, that's the direction that's actually going downhill, and there's only one force that acts in the downhill direction, and it is that component in the x direction for the weight. So we've got this component of the weight that is pointing downhill in the positive x direction, positive x. So this will be a positive mg sine theta. And that's it. That's all I have for forces in the x direction. You might be asking, well, what about A? A is not a force. A is an acceleration. So where should A go? Well, it should go at the very end of our summation. All of the forces acting in the x direction are responsible for taking our mass and accelerating it. And this is all I have along that x direction. This is all we get. And this makes it pretty easy to see what the acceleration down the incline is going to be, because all I have is mg sine theta equals ma x. I'm calling this a of x because this is the acceleration along the x direction, but as we said, all of our acceleration was going to be in the x direction anyways. But here we actually see the mass canceling out on either side, and that's it. This is the acceleration of our mass as it slides down the incline of value theta. And this is the reason why I did not provide us with any numbers to this system, is because we are getting what are called general solutions. This value for the normal force is accurate for any inclined system of any mass of any angle theta. All we have to do is plug in the values of the mass and the angles. And so if we were to bring theta down to 0, if theta was 0, well, we would just be back on a flat horizontal surface. And we already know what the normal force for that situation is. We've already gone through that problem. The normal force would have to equal the magnitude of the weight. But we can actually show that with this general solution. If we let theta equals 0 for the cosine, well, cosine of 0 is 1. And if cosine 0 is 1, then, well, there's our normal force. It's exactly what we need. Another extreme that we could try is instead of letting theta go back down to the ground, make this incline even steeper. In fact, make it so steep that the incline is 90 degrees. Well, what are you going to get for a normal force now if theta is equal to 90 degrees? Well, theta of 90 degrees, cosine of 90 makes for a 0. So does that mean that there's no normal force here? Well, look at it this way. Gravity always points straight down. And if gravity is pointing straight down, what is there to push the mass into the surface of the incline? There is nothing. And so if the mass doesn't push into the surface of the incline's not going to push back. And so we would have no normal force here. This block would just drop straight down. And we can play the same game over here with our acceleration. If we bring the incline down to a flat surface again, where theta is equal to 0, if theta equals 0, sine of 0 is 0, which means the acceleration would be 0. So how well is gravity going to accelerate this block in any given direction? And the answer is it won't. And that's because of that angle relationship. If we go over to this situation over here, where theta is equal to 90 degrees, sine of 90 is 1, and so the acceleration that we would experience would be that of gravity, but we kind of already know that. If we just hold this mass up against a wall and let go, it's going to fall and it's going to accelerate at a rate of g. These two expressions just allow us to calculate everything that's going to happen between those values of 90 and 0 degrees. And so now that we've done this, we really don't have to come back and do them again unless, and this is a big but here, unless there are other forces that are added into the system. If I add another force into the system, like maybe I start pulling up on this block with some force as it's traveling down the incline. Well, that would have to be an extra force that gets added into my equations, and as such, that is going to affect the outcome of this problem. And that's going to be the main focus of these next two chapters, is drawing out the diagrams, seeing the forces and the accelerations, and taking where everything is pointing, combining them with a reference frame to produce these summations of force. And these summations will in turn tell us what the other forces in the system are doing, how fast we're accelerating, which direction we're accelerating. And so we're just going to basically build upon all of these force diagrams and equations. And sorry to say, but the pictures are just going to get more complex from here on out. But we still have one more force to define, which is the tension force. But this particular video has already gone on long enough. So I'm going to go ahead and call it quits for here. I didn't realize just how much longer I could talk by going through this incline plane here, but this is not a bad thing. By being able to define and see how our normal force changes by placing it on an incline, that's actually going to be very useful to us in some of the future videos. So we'll wait for the next video to define the tension force, and then we'll start putting all of this stuff together into example problems, and then we'll continue on into chapter 6, introducing even more types of forces like friction and centripetal forces. So see you at the next video.